Hello everyone and welcome to the 12th and last part of the MOOC dedicated to hydrocracking. In the first part, the hydrocracker was relocated into the refinery and the reaction section was described. Then we talk about the fractionation section. Let's now have a look at the properties of the products and compare them to those of the FCC. Let's start with the fuel gas and LPG cuts. These cuts are H2S free since they have been washed with an amine. The main difference with the FCC is that these cuts do not contain olefins, so they are totally saturated. Indeed, the LPG cut of an FCC contains a significant amount of propylene, which will not be our case. In terms of mass balance, if you remember the MOOC dedicated to FCC, we said that we produced a quantity of fuel gas of about 5 tons per hour for a total feed of 150 tons per hour. In our specific case, we will produce 3.8 tons per hour of fuel gas, including 0.8 tons per hour of H2S. Note that in the fuel gas section of the FCC, we had about 71 weight% of C1 plus C2 and 28 weight% of C3 plus C4. In this cut from the DHC, we will have 25 weight% of H2S, 25 weight% of hydrogen C1 plus C2, and about 50 weight% of C3 plus C4. As far as LPG cuts are concerned, in the FCC we produced about 23 tons per hour. Here in the DHC we will produce 2.5 tons per hour. These two streams are almost exclusively composed of C3 plus C4. Light gasoline is completely sulfur-free, since it was produced in a reaction section in the presence of hydrogen. It therefore does not require any hydrotreatment. This stream has a run of about 80 and a density of about 0.65. It is a very paraffinic cut. Here we produce about 6 tons per hour. For heavy gasoline, it is quite similar as for light gasoline in terms of sulfur. I mean, this is an absolutely sulfur-free cut. Its density is about 0.74 and it is a very good naphthenic cut. So it will be a very good feed for the reforming of the refinery. Here we produce about 23 tons per hour of heavy gasoline. Here in the DHC we will produce about 30 tons per hour of total gasoline. Whereas in the FCC we will produce a mixture of LCCS plus MCCS plus HCCS of about 72 tons per hour. The kerosene produced in the DHC has very good smoke point properties of about more than 25 millimeters. The density is about 0.8 and the freezing point is very good, below minus 60 degrees C. No post-treatment is therefore necessary to reach the refinery's kerosene pool. The diesel cut produced in the DHC will have a very low sulfur content, just like the kerosene, and it will be lower than 10 ppm. The density is in the low range of the diesel characteristics asked by the regulation, here about 0.83. The cetane index is very good for about 60, and no additional treatment are necessary to let this diesel cut join the refinery's diesel pool. 58 tons per hour of diesel are produced in this DHC. For memory, in a FCC we produced a cut of LCO of 26 tons per hour. This figure shall be compared with the value of 58 tons per hour of total diesel produced in this DHC. Finally, the bottom cut, called here bleed, is a very paraffinic cut and has a very low density of about 0.83. Its sulfur content is quite low, lower than 100 ppm, and it is a very good feed for FCC, for example. We produced here about 20 tons per hour, where in the FCC we had a cut of unconverted VGO of about 16 tons per hour. If we summarize, here is what we get with an FCC, and here is what we get with the DHC in maximum distillate mode. The conclusion of this conclusion is that the FCC produces mostly gasoline. Note that about 95 weight% of the feed is converted into products. In fact, we produce 5% of coke, but this coke is self-consumed to satisfy the overall thermal balance of the FCC. Note that the products coming out of a FCC contain sulfur, nitrogen, aromatics, and olefins, and they all require downstream treatments. I invite you to watch the MOOC dedicated to fractionation section of the FCC. In a DHC, we convert about 103 weight percent of the feed into products. In fact, in a DHC, we consume about 3 weight percent in hydrogen. The products coming out of a DHC are sulfur-free, nitrogen-free, olefins-free, and they present a quite low aromatic content. They require very little or no post-treatment for all the products coming out of its DHC. On the other hand, it requires a substantial need for hydrogen, and this hydrogen is often produced from natural gas by reforming. Well, we are now at the end of this video about DHC. I hope that you learned many things about hydrocracking. In the meantime, like always, subscribe to my YouTube channel and answer the quiz. See you very, very soon for more videos in 2022. Bye bye!